Okay, today let's look at one-dimensional settlement of the soils. So in the past few weeks, we have been discussing geostatic and induced effective stress. Now we are ready to discuss soil deformation due to those stresses. So soil deformation is basically due to the vertical stress, and that will cause the settlement. So one of the things that geotechnical engineers are interested in doing is predicting how the soil is going to deform vertically when we apply the induced stresses. So those vertical deformations are what we refer to as settlement. There are mainly three types of settlement that occur in the soil. So the first settlement is what we call elastic or the immediate settlement. It is due to the elastic distortion of the soil particles themselves. So if we are looking at the solids of the soil, and if we load the soil of those solids, and the soils are going to deform elastically. So this type of settlement occurs instantaneously, typically right when we apply the load. So usually it occurs during the construction. It's the primary mechanism of settlement for coarse grained soil like sand and gravels. Now the second type of settlement that I have to introduce has to do more with the void ratio of the soil, and this is what we call primary settlement. So this is the most important part of the total settlement calculation. It may be so. Imagine if I had a sponge, and if I squeeze the sponge, it may be filled with water. All the water is sitting in the void space inside that sponge. So if we compress it, it has to push some of the water out. So it's the same idea with soil. If the soil is going to settle or compress, it does so by pushing the water out of the void space. And so there's a loss of volume in the soil. So depending on the hydraulic conductivity and the thickness of the soil, as well as the precision of the drainage layer, it could require anywhere between months to years for primary settlement to occur in a given soil. So this is the primary cause of settlement for fine-grained soils like clays or some finer silt. So this primary settlement, that's our main interest, and we need to pay more attention to it. And this caused the main settlement of the clay soil, and that's our that will be the target of our calculation. The last type of settlement is what I want to introduce. That's called secondary settlement. This is the settlement that occurs constantly over time, and it's due to the breakdown or degradation of decomposition of the soil particles themselves. So we get a long-term distortion of the grains, and it has the appearance like a plastic crepe type deformation. This type of settlements can occur years after primary settlement is finished, and they are particularly common in soils that have high liquid limit and water content, as well as the soils that are organic. So the soils like peat or other organic type soils, there's a lot of chemical decomposition going on, and that's changing the structure of the particles themselves. In this lecture, like I said, we mainly talk about primary settlement, but basically you need to know the total settlement is roughly the sum of the elastic settlement and primary settlement and secondary settlement. And primary settlement, as you can see from this chart, that's the main settlement of a soil layer. So here is an embankment built on top of few soil layers. So if the water is at the ground surface as shown here, normally the water can flow in the X and Y and Z direction. So here is an embankment built on top of few soil layers. So obviously, if the water table is here, then the water can flow in the X, Y, and Z direction. So consolidation is essentially three-dimensional. So however, due to the expansion of the soil in the horizontal direction, So water will not be able to flow out of the soil in the horizontal direction, which means the soil can expand long distance in this direction and also in this direction. So basically, the soil is mainly can flow out vertically or in the Z direction. So a general theory for consolidation incorporating the three-dimensional flow is complicated and only applicable to a very limited range of problems in geotechnical engineering. So for the vast majority of the practical settlement problems, it's sufficient to consider that both the seepage and strain take place in the vertical direction only as one-dimensional consolidation. So basically, our consolidation problem or calculation is mainly consider the settlement or the consolidation in the vertical or in the Z direction. Now let's have a look at the relationship between the volume strain and void ratio. So here there's a three-phase diagram of a saturated soil. So before deformation, we have the solid material with volume of Vs. So that's the volume of solid materials. And the void was fully occupied with water. So there's no air, and its volume is Vs times E0 because that's the definition of void ratio. So the total volume is Vs E0 plus Vs, and we can convert to total volume VO as the Vs equals VO equal to Vs times 1 plus E0. And after deformation, the water was expelled from the soil skeleton, and delta E will be the decrease in the void ratio. So the volume of the void becomes Vs times EO minus delta E. And total volume is Vs times 1 plus EO minus delta E. So by definition, the volume strain could be expressed as delta V, the change in volume to the total volume. So delta V divided by VO, and also we have the expression of VO. VO is the final volume V minus the initial volume VO. So that's the change in volume divided by original volume. And if we iterate the expression of V into this formula, eventually, and the Vs could be cancelled out, and we get this expression here. So for the confined compression, there's no strain in the X and Y direction. So the strain in the Z direction is equal to the volumetric strain. So in other words, the epsilon ZZ, the strain in the Z direction, equal to the total strain, the volumetric strain, epsilon Z. So finally, we get the vertical strain expression as negative delta E divided by 1 plus EO. So that's the this relationship will help us to calculate the settlement in the later part. So here is a soil with thickness of capital H. So if we apply the loading Q to its surface, it gradually settled. So obviously it gradually settled to the with the displacement of S. So that's the original soil surface. So when we apply the load and hold for a while, this is the final soil surface. So we know by definition, the vertical strain epsilon ZZ could be expressed as negative delta E divided by 1 plus E0. So from the micro view, we also know the strain that will be the length, the change in the length divided by the original length. So if you consider this as settlement as the length, so that's also equivalent to S divided by H, capital H. So the settlement can be calculated using the change in the void ratio, delta E, from the stress that was applied in this way. So S, so if we do the conversion from those two formulas, S equal to negative delta E divided by 1 plus E0 times capital H. And this H that's the original sample height.
Yeah.
So what is EO called?
EO, that's the original void ratio. So that's the void ratio before you apply some load. So in the lecture 1, you have some formulas. According to that formulas, you are able to work out the EO. All this EO, you can work out from the odometer test. You can take some measurement of the water content, then you can backward to work out the EO. So EO, that's the original void ratio. And this 30E, that's the change in the void ratio due to this loading.
Yeah, thanks.
Would delta E be the original height versus S?
Delta E?
Yeah.
Delta E, that's the change in void ratio. So if you apply some load, then the void ratio will gradually decrease. So that's the change in void ratio. And if this void ratio change, then if you look at the macro view, then there will be some settlement. So there's a corresponding relationship S and delta E.
Okay.
Yeah.
It's just I haven't seen delta E. I've seen the rest of them, but not delta E.
So delta E, later on we will just can just calculate this one using some other parameters I will show you later on. So yeah, so if it is unloading, then obviously there's no negative sign, and the soil will rebound in terms of increase in volume because this is loading. So obviously you have the settlement of the soil. And and also this change in void ratio, like I said, it could be derived from the consolidation curve. And also the settlement can be calculated using the change in void ratio from the stress that was applied. Sorry, any questions?
What about this negative sign? What actually it means? Is it decreasing or?
So this one that means your that means normally your delta E will be negative value actually. Yeah. So that will be because delta E. Let me just use a pen. So delta E equal to E final minus E1, right? Let's say. So this is change in void ratio. E final, because you apply some load, the void ratio will smaller than E1. Is that agree?
Yeah.
E1, that's so EF minus E1 will be negative value. Is that right?
Yes.
So negative, because negative, but actually when we express settlement, it's normally that will be positive value. That's why we have a negative sign here, so they can cancel out. So negative times negative gives you the positive settlement of the soil.
Yeah, got it. Thank you.
Okay. So now let's look at the rough procedure of the odometer test. So when we want to predict the properties of the consolidation settlement, there are two things we are really interested. So we are interested in how much settlement is going to occur. And we also interested how long it's going to take for that settlement to occur. So the way that we can predict this is we need to obtain a sample of the clay as undisturbed as possible and bring it back to the lab. And we are going to simulate loading it with an induced stress. So we take this clay sample and we stick it inside of a steel ring. So here you see we have a steel ring, and that's the intact soil sample. And then we put this steel ring together with sample inside a water bath. So this is normally the odometer testing apparatus. And we put below it a porous stone. This is a porous stone, and above it another porous stone. So these porous stones simulate the sand drainage layers. So the water that is being squeezed out of our clay sample can get out without a problem. And on top of the stone, we put this dial gauge here. And we are going to measure how much the soil sample consolidates or how much the sample settles when we apply the different amounts of load. This is called the odometer testing apparatus, and it often used to establish the void ratio versus effective stress relationship of a soil. So from this odometer test, we're able to get E versus sigma V prime relationship from the odometer test. And also one more thing I would like to mention that for the odometer test is always two-way drainage, because later on there will be lots of two-way drainage. There will be lots of assessment questions either in the final exam or in the quiz. It mentioned the soil sample in the odometer test with some given parameters, and then you are required to calculate CV all the time. So for any sample in the odometer test is always two-way drainage. So your maximum drainage distance will be the half of the sample height. Here you have to be careful. So that's some implicit information provided to you. For the odometer test, you see there's a porous stone on top and porous stone beneath, because this is to help to accelerate the drainage of the excess pore water pressure. Otherwise, if one-way drainage, it takes a longer time or few weeks or few months to drainage the excess pore pressure, which doesn't make sense. So this odometer test always two-way drainage, and you take the half of the soil sample for the calculation. Normally, for this calculation, you use TV equal to CVT. That's the last lecture, divided by D squared. And this D has to be the half of the sample height. So this is H, will be D equal to half H. So that's the part we need to be careful. And now, previously we already discussed the sample preparation of the odometer test in the previous slide. So once the testing setup is ready in the odometer apparatus, we start to apply a series of load to the sample. By saying a series of load, I mean just like 20, 40, 80, or 160 kilopascal. So you can apply another size of stage load, that's fine, but as long as maybe roughly doubled each time for each increment. So for each load increment, we take the stable settlement, which means we apply the load and we hold it for a while until there's no change in the dial gauge readings, and we take that readings as a record. And normally we double the loading each time, and sometimes we conduct an unloading and reloading loop with a final unloading stage. So this is so if we look at this chart, it's always the loading part. So with the increase in the load, your effective vertical stress increase and your void ratio gradually decrease. So that's a common sense. And then by the end of the loading, you just gradually take out some load. So and the void ratio gradually increase. If you look at the vertical axis, that means there's a rebound in the for the soil sample. So that's the reverse of the settlement. And at the end of the test, we remove the sample from the apparatus and measure its water content. So, and then from this E equal to W times GS, if we measure the water content for a specific type of soil, we know it's GS, so we can work out the void ratio. So this is the final void ratio of the soil sample. And also based on the height change of each increment, and according to this relationship, delta E divided by 1 plus EO. So the final void ratio at the end of each increment can be found accordingly. So we know the final soil sample height. We know the height change, and if we also know the change in the void ratio, so we know, so we can work out the void ratio after the end of each increment. So basically, we could obtain the void ratio at the end of each increment, and we are able to plot the void ratio E versus sigma prime on this semi-logarithmic scale axis. So the horizontal axis of this chart is always in the logarithmic log scale, so the horizontal axis. And vertical axis, the void ratio is always the normal scale, the linear scale. So a typical profile is shown in this figure. and we have the curve for loading here. The water ratio decrease, and that indicates the settlement of soil. And this is the curve for unloading. This is the curve. And we can see the water ratio increase with unloading, and it's an indication of the rebound of the soil. So this is a typical water ratio and effective stress relationship. So water ratio E, again, the effective stress that's in the log scale. And it's normally this OPR, this line is the virgin loading curve, and this QP is unloading and reloading curve. So we can see from the figure that for the same amount of change in vertical effective stress, so if we always change the effective vertical stress from the original one to the final one, then the change in water ratio depends on whether virgin or unloading or reloading curve is used. If we use this virgin curve OPR, then you can see the corresponding change in water ratio is this high. That's the change in water ratio. If we use the unloading and reloading curve, then that's the corresponding change in water ratio. In other words, this depends on the stress history. So those are very important indication for the later conclusion. Now let's look at the stress history. Here we have the definition of the pre-consolidation stress, or the pressure. So this one, the maximum vertical effective stress that the soil has ever felt in its existence, as long as the soil has maintained its soil fabric, is called pre-consolidation stress. And it's a record of the highest stress the soil has ever felt. So for the soil on the virgin loading curve, OPR, the pre-consolidation stress equals to current effective stress, sigma prime. And for the soil on the reloading or unloading curve, QP, the pre-consolidation stress equal to sigma P prime. Useful in the later part, we have decided where is the pre-consolidation stress. So here we have to be careful. If it's on this line, then your calculated stress equals to the pre-consolidation stress. Your calculated stress, that will be the consolidation stress. If your point falls on the reloading, unloading and reloading curve, then your pre-consolidation stress will be the maximum point of this curve. So it will be the intersection point between the QP and OPR. So that's the point P. We always talk about normally consolidated soil and overly consolidated soil. So here are the definitions. So if the current effective stress sigma prime is equal to the pre-consolidation stress sigma P prime, then the soil is said to be normally consolidated soil. We call it NC soil. It is the first time that the soils are loaded to the present applied effective stress, and the normally consolidated soil has the higher settlement. If we go back and to check the previous slide. On the other hand, if the current effective stress sigma prime is less than pre-consolidation stress, so sigma prime less than sigma P prime, then the soil is said to be over-consolidated. So normally we use the OC to stand for it. OC. Sorry. This means the soil are already loaded in the past history, and those soils are less compressible and more stable, which means there are less settlement for over-consolidated soil. So in the field, what we need to do is we try to create more of the over-consolidated soil. So later on, when you apply some load, there will be less settlement, and if you construct some structures on top of the soil. So if you construct any structures on top of the normally consolidated soil, then it's more likely there will be more settlement to occur. So here we have to be aware of the definition of the normally consolidated soil and overly consolidated soil.
So
Yeah.
so like, can we have this relationship if we have the current greater than the pre-consolidation stress? Can we do that as well, or we can't?
No. If current greater than that one, that means your current will be equal to sigma p prime.
Oh, okay.
Yeah. So because this sigma p prime is always the maximum effective stress that the soil has experienced. So if the current one is greater than the one, then automatically the current one will be sigma p prime.
Yeah. I see. Okay, sweet.
That's a good question. Yeah.
Thank you.
So it will be come to the normally consolidated soil.
Yeah.
Okay.
Is that the point on the graph where the 2 points meet?
Which one? This one. Yeah. That's one sigma p. If OC soil, it will be like that way. If it's OC soil, so OC soil is always here in the unloading and loading part, and NC soil is always here. So if where the 2 curves meet, that will be the sigma p for the OC soil. Okay. This is OC, this is NC. I will just explain in more details in the later part, because here that's really important for this lecture.
Okay.
Okay. So I have 2 types of clay. I have over-consolidated clay, meaning that the soil has felt a larger amount of stress in its past and it's feeling right now. Or I have normally consolidated clay, which means the soil is currently feeling the largest amount of vertical stress it's ever felt in its existence. So normally there are two types of clay soils. We can see from this figure that for the same increase of vertical stress from sigma O to sigma P, sigma O prime or sigma P prime, the change in the water ratio for over consolidated soil, OC stage. So this is unloading and loading curve, and we also normally call it OC soil. So if we check this curve, you see that that's the change in water ratio. We already briefly discussed previously. And that's the NC stage. That's the NC. So for the same change in the vertical stress, we can see the change in water ratio for the OC soil is much less than the change in the water ratio in the NC soil. So this means in the field, most soil are overly consolidated in some extent. So the settlement will be much less than the corresponding normally consolidated soil. So the conclusion is settlements will gradually be much smaller for structures built on over-consolidated soil. But actually in the field, a majority of the soils are overly consolidated, which is good thing, because this is due to the shrinkage or swelling of the soil out of draining and reweighting. And also, if there's any erosion of the overlying strata, then it will also cause unloading and creates over-consolidated soil. So for the E log sigma curve, the distance from the virgin curve has an important influence on the soil behavior, and it's normally evaluated by the OCR. So this is another important calculation definition. So the over-consolidating ratio, or OCR, is defined as the ratio of pre-consolidating stress to the current effective stress in the soil. So if the current effective stress is equal to the pre-consolidating stress, then obviously the OCR is 1, and we say the soil is normally consolidated. So this is for NC soil, the OCR equal to 1. And on the other hand, if the current effective stress is less than the pre-consolidating stress, then the OCR is going to be greater than 1, which means the soil is overly consolidated. So for the LC soil, the OCR is greater than 1. So that's the conclusion we can draw from the definition. So through the lab test, we could only get the curve QPR. So basically, if we just check the previous testing curve, odometer testing curve, normally we only have the QP and PR. Hardly we can get this OP curve, and this PR, that's the normal loading curve, and this PQ will be the unloading curve. So because why we don't have this OP1? Because during the retrieval of the samples from the field, there's already an unloading process. So hardly we could get the curve OP in the chart. So normally we just consider the QP and the PR curve, and this PR that's normally for the normally consolidated soil or the normally consolidated stage, and this PQ that will be the overly consolidated stage. So in order to calculate the settlement, we need to estimate the pre-consolidated stress first. So we need to work out the sigma P prime first. So here we have a Casagrande method to estimate the pre-consolidated stress sigma P prime. And this is a graphical procedure for us to find the pre-consolidated stress. And this is a typical testing curve from the odometer test. Let's say if we run odometer, we take the different void ratio, and we also know the corresponding the load on top of the sample, so we can work out the effective vertical stress. If we just increase another add another increment, then the void ratio decrease. We can work out the corresponding void ratio. If we do the same way, we get a series of points, and if we connect those points with a smooth curve, we get this E log sigma prime. Well, the purpose of doing so, one purpose of doing so is to derive this pre-consolidation stress. This is a typical testing curve from the odometer test. So firstly, we find the point A, and this point A, that's the point that represents the maximum curvature of the curve. So obviously, roughly this point, that has the maximum curvature. Then we draw the tangent line AB to this curve. We draw a tangent line, and so the AB is shown on this chart. And then through the point A, we draw a horizontal line AC. So this is a symbol. We just draw a horizontal line. And next, we are going to look at the angle between AB and AC. So this angle. And we are going to draw another line, AD, which is the bisector of the angle BAC. So this AD, that will be sitting in the middle of AB and AC. Next, we extend the original. So you see that's the original line, that's the QAP. Next, we extend QAR. Next, we attend the final straight line part of this curve backward. So we are able to get line RE. And this line RE is a straight line. And eventually, if you intersect this line AD at some point P here. So the corresponding stress at point P is the so-called pre-consolidation stress of the soil. So this is the Casagrande method to get the pre-consolidation stress of the soil. This is a rough procedure or the graphical procedure to get sigma P prime. This is only for your information. So for the original E log sigma prime curves, they could be idealized as straight lines. Previously, we have, you see, it's a bit curvy for the QP and PR curve, but we can simplify it as a straight lines, two linear lines, QP and PR. And also for the each line, we have the slopes. Obviously, we have slopes C sub R. That's called recompression or rebound index C sub R. This one. And it's the slope of the unloading and reloading curve. So this one is equivalent to this one. So that's for the over consolidated soil stage. That will be the gradient of the over consolidated soil stage. And C sub C, that's the, we call it compression index, C sub C. And it's the slope of the loading curve or the slope of the virgin compression line, NC line. So normally, for the majority of the calculations, we just we can find corresponding value of initial stress, the pre-consolidated stress, and final stress. If we know the relative position, then we are able to choose the corresponding formulas to do the calculation. So these are what we call the settlement parameters, C sub C and C sub R. And we are going to use these parameters to predict the magnitude of settlement that we are going to get from some induced stress that we applied to the soil.
Excuse me, sir.
Yeah.
The CC curve, the CC ratio is saying the compression index, the slope of the loading curve.
Yeah.
Is it the loading? Is not the QP is the loading or unloading curve?
QP is the loading and unloading, and CC, that's the original compression curve. So C, you see C, that's the compression, and R, that's the recompression. R stands for recompression.
Okay.
What do you mean by unloading? Is that when you take the pressure off?
Yeah, that's right. That's right. So you see, for the real scenarios, you see, you have some pressure, right? You have some pressure out of the maybe construction. You have the Q here, and later on, maybe you may gradually reduce the load or totally remove the load. Then surely you have some unloading occur. So this will be the unloading curve. If you take the load out, then the soil will rebound. So that's what this curve and gradient represents for.
Okay, thank you.
Yeah. Now we just came to the main part. So for the curve QP and OC strength, QP and PR, the stress range, the CR. So let me say it this way. So for the majority problem, we can just draw a compression line here. So that will be the original compression line. And we also have the, if you just unload from any point, if you just follow this trace back. So let's say you have original PR line, and if you unload from the P, then surely your unloading curve will follow the PQ and this way. So normally for the majority problem, we have a whole curve that was composed of two segments, and the PR that represents the OC stress range, and sorry, the QP that represents OC stress range, and this PR that represents the NC stress range. And if you look at this figure, because due to the geometry definition, we know the slope of the line. We can work out the CR. So CR will be the change in the void ratio divided by the change in the vertical effective stress. So CR equal to negative 30E divided by log 10 sigma 1 prime minus sigma O prime. So that's the definition of the gradient. Is that clear? So CR will be equal to Y divided by X. So that's the gradient of this curve. And also this Y will be equivalent to E1 minus EO divided by X. X will be log sigma 1 prime minus log sigma O prime. So if you do the conversion, it will be 30E divided by log sigma 1 divided by sigma O prime. And then if we would like to express the 30E, the change in model ratio in terms of CR, here is how it looks like. We move the 30E to the left-hand side and CR to the right-hand side. So we are able to express the 30E, the change in model ratio in terms of CR and the original and final effective vertical stress. So that's the OC stretch range or the QP part. For the NC stretch range, so similarly, we are able to work out the CC formula, the CC in terms of change in model ratio and also the change in the vertical effective stress. So if we do the conversion, we can also express the change in the model ratio in terms of CC. That's this one. So this is scenario 1. So normally for the calculation, we have 3 scenarios. So firstly is all the change in the effective stress all occur in the OC range. Then you use this formula to do the calculation. If all the initial stress and final effective stress all in the NC range, then we use this formula. So we also have a third scenario, which means the effective stress, the initial effective stress is within the OC range. And finally, when you apply more load, the final vertical effect stress will go to the NC range. So that's called the stress range from the OC to NC. We call it the third scenario. So obviously, for such calculation, we need to calculate the void ratio change. Void ratio change from this part to this part, and also the void ratio change from this part to this part. So if we look at vertical axis, so that's the void ratio change in the OC part, and that's the void ratio change in the NC part. So eventually we have to sum all the void ratio change together. That gives you the total change in void ratio. But now that's only the change in the void ratio. We have to cover, because with this lecture, we mainly concerned about the change in the settlement. So we have to set up the correlation between the change in void ratio to the change in the settlement. So here we are. Also from the previous few slides, we already know the settlement equals to negative the change in void ratio divided by 1 plus the original ratio times the sample height. So if we iterate the expression of 30E in the previous slide into this settlement formula, there are 3 types of cases of calculation for consolidation settlement. So this is already discussed. So for over consolidated stretch range, that's both the initial and the final stress are less than the pre-consolidation stress. We use this formula. So this 30E comes from the discussion from the previous slide. So eventually we have this formula. And also I'd like to say, so for these problems, you see, you can always plot those 2 line segments. And this part will be the sigma p prime. It's always like this way. And this is the OC. This is the NC stage or OC stage. So over consolidated stress range means your effective EO, effective stress and final stress all within this part. So sigma, let's say maybe sigma 1 prime and sigma f, maybe sigma f prime. So your effective and your final effective stress all within this OC range and all less than the sigma p prime, then you use this formula to do the calculation. So that's the first scenario. And second one, let's say now my effective vertical stress comes from here. So that will be the sigma 1 prime. And my final vertical effective stress comes from here, sigma f prime. So both sigma 1 prime and sigma f prime are greater than the sigma p prime. Then we use this formula, the second formula, this one. Normally, because that's all the normally consolidated stretch range. And finally, we have the third scenario. So 1, 2, 3. Let's say maybe. So my initial vertical effect stress is here. So that's in the OC range. And my final vertical stress, that's greater than the pre-consolidation stress. So that's in the NC stage. So my calculation of the settlement, it has to be composed of two stages. So one is the settlement from here to here, and the other one is the settlement from here to here, and sum. I need to sum them together. So that's the two segments or two parts of the calculation, and we sum them together. So now it's a bit, as I hope it's already a bit clear to yourself. So for this type of consolidation settlement, you only need to work out the initial effective vertical stress, the final effective vertical stress, and also the pre-consolidation stress. And then you plot these two line segments to find the corresponding position of the initial and final vertical effect stress point relative to this pre-consolidation stress. Then you are able to find the corresponding formulas to do the calculation. So these formulas are really important. That's the most important part of this lecture. So you need to know the relative position of these 3 points and then find the corresponding formulas to work out the settlement. So for the calculation of the settlement, here are some points to note. So normally we need to find the initial, the final vertical effective stress and the pre-consolidating stress, and then we will know their relative position, like I said before. So we need to know the sigma O prime or sigma 1 prime, sigma F prime. So that will be the final vertical effective stress, and sigma P prime, that will be the pre-consolidating stress. We need to do the calculation for those 3 points, and we know which one is greater or their relative position. And then the initial stress can be calculated from the weight of the overlying soil or the self-weight of the soil. So if you normally for this type of questions, so the gamma, or is gamma SAT or gamma prime or gamma D. So the unit weight of the soil is normally given. So you are able to work out the initial sigma O prime, the initial vertical effective stress. So sigma O prime equal to gamma times H. So here you have to be careful. Sometimes if you have water table, then you need to consider either use the submerged unit weight or effective unit weight. If there's no water table, then you just use the either saturated or the dry unit weight according to the different type of soil. And then if there's any change in the pressure, in the position of water table, then the initial and final pore water pressure can be determined accordingly. So the pore water pressure is only correlates to the position of the water table. So why we mention this one? Because sometimes you are not able to work out the effective stress straight away, but you need to work out or calculate indirectly. So total stress equal to effective vertical stress plus pore water pressure. Also, you need to find this effective vertical stress either for the initial or the final or the pre-consolidation stage. So if you know the total stress, you know the pore water pressure, you can just work out backward. So that's what it means here. And we also need to find the increase in total stress due to the applied load to work out the final total stress. And finally, we calculate the settlement of each sublayer due to previous formulas and add them together. So that's a few points we need to consider during the calculation. Now let's look at the general procedure. So there are mainly 5 steps for settlement calculation. And step 1 is to divide the soil profile into a number of sublayers. So this one, obviously, the information is already provided in the question. So sometimes you have a gravel layer on top of clay and underneath is sand. So obviously there will be 3 layers, something like that. And step 2, we need to calculate the effective vertical stress, sigma OI, for each sublayer. So we need to work out the initial effective stress for each sublayer. And then we calculate the final effective vertical stress in each sublayer as well. So the final effective vertical stress will be the initial effective vertical stress plus the increase in the effective vertical stress. Or the final vertical effective stress, sigma Fi prime, also equal to sigma Fi minus U. So this is direct way to do the calculation, but some other cases we may need to do the calculation indirectly if there's any information about the change in the water table.
Excuse me, sir, how to calculate the initial? Is the sigma prime is equal to the gamma time height?
This one?
Yes.
So this one, you see, we already practice a lot. Let's say, you see, if it's sand soil, so sigma OI. So let's say if it's sand, then sigma OI will be gamma times H, this layer height. And this gamma will be gamma D, because the sand is normally, if there's no water table, that's a dry unit weight.
But if there is a water in the sand, then is it saturated?
No, it's water. Then you use effective unit weight, gamma H. You use the effective unit weight, gamma H.
Thank you.
Yeah, or just saturated unit weight minus the effective unit weight of water times H. So you see, if you go back to the tutorial, I think maybe tutorial 3 or 4, we have lots of practice to work out the effective vertical stress of a soil. Yeah, and then step 4. Is to calculate the settlement of each sublayer. So for each sublayer, we just refer to this formula, but actually they are equivalent to this one. So mainly we need to use this formula to do the calculation. So that will be the settlement calculation of each sublayer. So you can see the threshold. So this one, again, you see, if once you just work out sigma OI prime and sigma P prime and sigma Fi prime, you just plot the 2 segments like what I plot. So this one stands for OC, this one stands for NC, and this will be the sigma P prime or sigma Pi prime here. So if your sigma Fi prime less than that one, so which means, what's that mean? Sigma Fi, that's the final vertical effective stress of that sublayer. That means, you see, that's in the OC stage. Then you just use this formula to do the calculation. Or if your initial vertical effective stress already greater than this one, and that's in the NC stage, then you use this formula. So otherwise, if the initial, if less than the sigma P prime, and your final point that's greater than sigma P prime, then you use this formula. So basically, there are just only the three scenarios for you to do the calculation. So that's a really important formulas for this lecture.
Are we going to do any examples of this?
I think so. Yeah, in the end of this lecture, we have just one example to practice this one.
Okay.
Yeah.
Excuse me, sir, could you go back, please?
Mm.
So here at the first stage, when the final of the sigma is just less than this, is we are in OC stage, yeah?
You mean this one here, right?
Yes, yes.
Yeah, that's OC.
And the second one, when O01 is greater than
The pre-consolidation strength.
So we are in NC stage here, yeah?
Yeah, you are in the NC stage. So
And
this
otherwise
means,
is
sigma OI prime less than sigma PI prime and less than sigma FI prime. So this one actually mainly based on the assumption that sigma OI prime is always less than sigma FI prime. So you always apply some loading on top of soil. So because if you need to do the calculation. So first relationship, sigma OI prime, initial vertical effect strength is always less than the final vertical effect strength. Okay, this one. And then
yes.
If your final is less than the sigma P prime, that means your initial one is also less than sigma PI prime. Does that make sense?
Yeah.
Yeah. So your final is less than this one. That means your initial, because your initial is always less than final, your initial will be smaller than this one as well. Then you go for this OC formula. So this is called settlement of over-consolidated soil. You use this one. That's the first case. Second case, if your sigma OI is greater than sigma PI, which means your sigma OI ends up here, right? Somewhere here.
Yeah.
And your sigma FI always greater than this one, then your sigma FI will be here, somewhere here, right?
Yes.
So it's always NC soil in the NC part, OC part. Then you use this formula, NC formula.
Yeah.
Yeah. And then the other case is your sigma OI, the initial vertical effect strength is less than this one, and your final vertical effect strength is greater than this one, than this pre-consolidation strength. So you have 1 point less than sigma PI, 1 point greater than sigma PI. Then you calculate the two segments and sum them together. So that's a OC plus NC.
Okay.
Yeah.
Thanks.
So majority problem is always falls in any of these three scenarios. So here you have to be careful about their relative precision. That's what I call work out those three values first, and then find their relative precision in this two line segments, and then find the corresponding formulas to do the calculation. Once you fully understand this, I think the calculation will be quite straightforward. Just work out the value and plug into the value, plug into the formulas. Normally, those CC and CR are provided in question, so you don't need to worry too much. And the only and this HI, that will be the height of the each layer. So that will be surely that will be provided as well. So you only need to worry about this one using sigma OI, sigma FI, or sigma PI. So again, those three values, and this void ratio, is either will be provided or you can work out indirectly from the formulas you learned from the first lecture. We will have just one practice for this to make use of those formulas. Hopefully you can fully understand by now. The final step is to sum the segment of each sublayer. So by now we have learned two formulas two methods to calculate settlement. So S equal to MV times the sigma prime times H. So this is the first important one, and that's the second one. So this is one that's a really important formula we learned from the last lecture, lecture 9. So normally you have to work out the vertical effective stress increase for the two conditions. So before you apply any stress or before any water table change, and after you apply some stress, and after you apply some stress, or after the water table changes. And normally the MV that will be provided, and H again, that's the soil layer height. So if we look further, you will notice that so both MV times the sigma prime and delta E divided by 1 plus E stands for the strength sigma V prime. So both methods are essentially the same. They are essentially the same. So the formulas in the lecture 9 and in this lecture, they are the same. Now let's look at one example. I think that will be the last example of this lecture. And actually, this example that's the same as the one given as the lecture 9. There's only slight difference in the initial condition. So it's here. The pre-consolidation stress at A that's already provided. The pre-consolidation stress at this A. So sigma P prime is already provided as 120 kPa, and the soil is normally consolidated at B. So that's the NC soil for the B. So that's the two additional information compared to the initial conditions in the lecture 9. So if I look just briefly, so we have a water table here, and you have gravel 2 meter, and below it 3 meter gravel, and then 4 meter of sublayer, subclay layer, and then another 4 meter subclay layer. So if the water table rises to the surface of the gravel gradually over a period of time, and surface loading induce an increase of total stress of 100 kPa at point A and 60 kPa at point B, we are required to calculate the settlement of soil, and gravel here is the information, the saturated unit weight and dry unit weight, and for the clay, the water ratio, the specific gravity, the CC and CR are given. So again, for the settlement of such soil stratigraphy, those are the gravel, as we discussed, there are only some minor elastic or immediate settlement occur. So, and those settlement, amount of settlement, we can just ignore that. So we don't need to worry about the settlement of the gravel layer. We only need to worry about consolidation of the clay layer, and that's the so-called the primary consolidation, and that's what we are going to calculate, because that's settles a lot compared with the immediate or the secondary settlement. And also for this type of settlement, we have to again we need to calculate in the middle point of each sublayer, and that's the settlement of middle point that represent the average settlement of that sublayer. So again, this is a diagram of soil stratigraphy and the corresponding given parameters. So we need to be aware that there's a stress increase if we apply some load on top. Once we apply some load on the top, according to what we learned from the lecture 8, the stress increase. So if you generate some stress increase, you see, and we are able to work out. So it's either the rectangular or circular loading. Then we are able to work out the stress increase, corresponding stress increase for any particular depth. And then if we connect those magnitudes together, we get roughly a smooth curve like this way. So it's always close to the loading position, the greater the vertical stress increase will be. So the further away from the loading point, the less the vertical stress increase. So, and this one, you see, if we apply some load on top of the ground, and then it generate some vertical stress increase at, actually it's a 7 meter below the ground. So 5 plus 2, 7 meter below the ground. So it generates stress increase to sigma of 100 kPa. And if you just, we just go further, it so if 5 plus 4, 9, and plus another 2 meter, because that's the middle of this clay layer. So for 11 meter below the ground surface, it generates some stress increase at 60 kPa. So that's some information that's already provided in the question. So now, because we are trying to just use the formulas we learned in this lecture, so obviously what we need to do is we need to work out initial, so sigma O prime and sigma P prime and sigma F prime, and then find the relative position, and then plug into the 3 sets of formulas to calculate the settlements. So that's our target. But before that, we need to collect all the given information. So for the initial vertical stress calculation, obviously we need to know the submerged, we need to know the unit weight of soil. So firstly, we need to calculate the saturated unit weight of clay, and that's the formula we learned from first lecture. So this is the repeat, actually the repeat of the content in the first lecture. So we know the GS, we know the mold ratio, and submerged unit weight of water, that's 9.81. And we can easily work out the saturated unit weight of clay, that's 19.06 kilonewton per cubic meter. And then for the initial state at point A, so we work out the total strength. So total strength, that will be the gamma H. So if we dry soil, then we just, if there's no water, then we just use the dry unit weight. So 18 times 2 plus 3 times 22, because 22, that's the part, that's 3 meter gravel, that's below the water. And then plus 2 times 19.06, so that's the unit weight of clay, because this is total strength. So what we calculate, that's the effective stress equal to total stress minus pore water pressure. So we calculate total stress at this stage. So if you can do the other way, effective stress also equal to gamma H, and this gamma is either gamma prime or gamma D. So you can do either directly, so or indirectly. I think in the previous tutorial, we already practiced a lot. So one is the direct way, the other is indirect way. Now we just go for indirect way. So that's the total stress for the first subclay layer, and then pore water pressure. So for the middle of this clay layer, so obviously that's 5 meter below the water table. So pore water pressure will be gamma W times H. And we get,
so,
yeah.
In the question, he said that the water table is 2 meters below the surface of the gravel. Does that mean the H is 2? Like,
No.
instead of 5?
No, because that's because we try to work out the, you see, the initial vertical stress and final effective vertical stress and pre-consolidation pressure at the 2 sublayers. So we only need to calculate the middle point of each sublayer separately.
Yeah, I know.
Yeah. So water table will be relative from here to here.
Oh, okay. Yeah.
Yeah. So all the calculation correlate to here, to this point. It's not related to the water table, to the ground surface.
Okay, cool.
Yeah. So
Yeah,
it will be, yeah, it will be 3 plus 2, and that's why it's 5 here. Yeah.
Yep.
Yeah. Good question. So the pore water pressure has 49.05 kPa. Note of And then effective stress, that will be the difference of total stress and force pressure, and we get 91.07 kPa. So that's the indirect way to work out the effective stress. But we can also do it in the direct way. Then you realize they end up for the same answer. So you see, now this one, this sigma ZZ initial prime, that's what I call the sigma O prime. So those are the general or the general term. So sigma O, that stands for the initial, F for final, sigma P, that's a pre-consolidated pressure. Now this one, that's 91.07 kPa. So if we just, yeah.
Which is less than 120 kPa, that's why it's in a OC stage, yeah?
Yeah, that's a really good point. So you see, that's what I'm trying to say. You see, the pre-consolidated stress is already provided as 120. So which means now we need to do the comparison. Sigma P prime equal to 120.
So can I ask you a question?
Yeah.
You go direct, find the, what is it called? Effective stress, this one. If we multiply the dry unit weight times the H, it will give you only 90. Will that matter?
Which one?
It will be 18 times 5, right?
Let me see. It will be
The answer
anyway.
will be
No,
90.
no. 18 times 2 plus 18 minus, sorry, plus 92 minus 9.81 times 3, and then plus 19.06 minus 9.81 times 2. So if you sum those three expressions together, it will be the same value. It won't be different.
It's more confusing. All right.
Yeah. So 18 times. So if you, because if you do the direct way,
Because
I mean,
here is the dry unit weight times the H.
no. This one maybe a bit cause confusion. That's why I write, you see, either gamma D or gamma prime. So if there's no water, you use gamma D. So above water, and for sand or gravel, you use gamma D. Below water, you use gamma prime. So that's what I did. You see.
Yeah.
So below water.
Just stick to the other methods.
Yeah. So is that clear? Maybe let me just write maybe clearly. So 18 point times 2. So that's above water. So that's dry soil. And then you sum 22. Because you use saturated minus the unit weight of water. So 22 minus 9.81 times 3. So that's the calculation of gravel stage. And then calculation of the clay part, that will be 1906 minus 9.81 and times 2. So the answer will be the same, 91.07 kPa. So those practice, I think we already practiced a lot in the lecture 3 or 4. But the main part, what I like to mention is here. The pre-consolidation stress is already provided. So what we can tell right now, again, you see, we plot the two line segments here. So now sigma P is already here.
Okay, so for the third layer, why we times 2, not times 4?
Which one?
Why we took like the half distance? And like the first we took 2 meters, then 3 meters. Then in the third one, it's 4 meters, but we took the half, we took times 2. Why?
No. If we take 2 is always because for the settlement calculation, for the top of the clay layer and for the bottom clay layer, always maybe the top part will be greater. So actually your real settlement, that's a good question. So for your real settlement, it will be like this if you draw the settlement curve. So normally if we take the middle, it stands for the average settlement of that soil layer. So that's what we normally did. We not always take the middle of the soil layer to do the calculation because yeah.
So sorry, when we always take the halfway, when it's what, like what's the condition when we take it?
No, if you use these formulas, the formula we learned from this lecture is always you take the half of soil layer, half of the clay layer. It's always do the calculation in the middle of the clay layer.
Okay, thank you.
Yeah, and since the sigma O prime that's less than the sigma P prime, so you see obviously that will be the initially the over consolidated soil because we falls in the OC state. You see OC state. Now we just do the calculation for the funnel part. So this stress increase I already discussed previously. So that's a 100 kPa stress increase, and the funnel total stress, that's the funnel total stress value. And pore water pressure, since the water table runs to the top of the ground surface. So now the distance will be 2 + 3 + 2. So that will be the 7 meter. So that's the pore water pressure value. And then effective stress. So that's the value for the effective stress. I call it sigma funnel. So now if we plot this one again, so sigma P prime, that's 120, right? And sigma O prime, that's around 9107. Probably I have this chart. It's here. It's already here. Can just remove this? Yeah, it's good. So now again, so that's now we just go to find the relative position of the initial, the funnel and pre-consolidation stress. So that's the 29. So if we label the values in this curve, so it's always like this: the loading and unloading curve, and the pre-compression curve, or the NC/OC curve. So we can see that the soil in the first sublayer moves from being over-consolidated to normally consolidated, because the sigma O prime, that's the one we calculated before we apply unload and before the water table raises. And this 120, that's the given value. So it's always the intersection point between NC and OC. And this is the sigma F prime. So that's the value we work out after we apply the load and the water table rises. So now, so which scenario this one belongs to? So this belongs to the scenario from the OC soil to the NC soil. So obviously we need to use the third or the last sense formula to the calculation. So we need to calculate the change in water ratio in 2 stages, or both over consolidation stage and also the normally consolidation stage. And we are going to use the third formula in the previous slide. Is that clear? This one?
Yeah, I'm not understanding the graph properly, because the values are increasing, yet the slope's decreasing. I'm not sure how you've done that.
No, you see, for all these problems, it's always one is the normally consolidated. Normally consolidated, the gradient is always greater than the over consolidated. So when you just have an assessment, you always plot the 2 curves in this way. This is for NC, this is for OC. So this is sigma P prime. This will be the sigma F prime, and this is the sigma O prime. It's always like this. So because the gradient, that will be reflection of the change of the settlement. So previously we already seen that the NC soil, it has higher settlement. Why is that way? Because the gradient is higher. So that's why the change in water ratio is much larger. So you have a higher settlement. So what we need to do, just work out the 3 values and find the relative position and choose the corresponding formulas to do the calculation.
Excuse me, sir.
Yeah.
Could you go to the 1 slide back, please?
Which one?
So when we calculated the final stage at A, like the final, the water level goes up. Why?
No, this is a given condition.
Where is C?
No, the given condition is 1, the stress increase, and 2, water table change. Okay, maybe you just go back your own material. I have to just finish this one and maybe do a summary. So finally, when we just if we use this formula, we can easily work out the settlement. That's a 0.09 meter. So that's the total settlement of the first sublayer. And for the second sublayer, so for the point B, the initial vertical effect stress. So again, so that will be the difference of the total stress and port pressure. So if you are familiar with the first sublayer, then you can easily work out the total stress and port pressure, and the difference of them, that's the effective vertical stress. And this is indirect way. You can also use the direct way to calculate the effective vertical stress. And also is also provided. So this is a given condition. Initially, the water, the clay soil is normally consolidated. So finally, when we just after we apply the load, apply the pressure to the soil, and also the water table rises, we can work out the total stress. That's the value. Don't forget to plus this 60. So that's the given condition. And port pressure. So now we are in the middle of the bottom clay layer. So that will be 4 plus 3 plus 4 plus 2. That gives you the 11. So 11 meter height from the water table to the current position of interest. So again, the effective stress, that will be the difference of initial and of the total stress and port pressure. So this means, what's this mean? This means the clay in the layer 2 remains normally consolidated. So both are in the normally consolidated part. So we can use, if we pick, then we are able to use the second
case 1.
set. No, I think that's a case 2. Case 1, that's OC.
Case 2,
Case 1, that's the NC. Case 2, that's OC. So yeah, so we plug in all the values.
So case 1 is OC.
Yeah, case 1 OC.
This is NC. Yes.
Yeah, this is NC. So we are able to work out the settlement of the second sublayer, and that's the total settlement. That's a 0.15 meter.
So can you go back 1 second? Just this, what does this 60 come from?
No, you see, that's the given condition. That's a given condition.
It's given.
Yeah, it's given.
All right, no problem. Thank you.
Yeah, if you review the last lecture, you will see it's all. This is the same as the last one. Some condition.
The load going down.
Yeah, you have some load on the surface.
Yes, Q.
Yeah. You have Q.
Okay, yeah.
Your Q, you have Q on the surface, but you generate some stress increase, like I discussed in the previous slide.
Yeah,
so the stress increase at A, that's 100, and the B, that's 60.
Yeah,
that's where 60 come from.
Yeah, no problem. Thank you, sir.
Let me see. So for all these type of questions, so you see, don't be panic. So you just work out the sigma O prime and sigma P prime and sigma F prime, and always plot those two line segments and find its relative position. So if the sigma O prime and sigma F prime all less than sigma P prime, maybe let me just use this one. You see, if all less than sigma P prime, use this OC formula. If greater than sigma P prime, use NC formula. I mean the both value, both sigma 1, sigma O and C final. Otherwise, if one less than sigma P prime and the other greater, if one less than the pre-consolidated pressure and the final greater than pre-consolidated pressure, then use this one, those ones.
Excuse me, sir. So if unluckily we got whatever the sigma initial or final prime comes to exactly the sigma P prime, the value comes same at the middle.
Yeah.
So what should we do that?
Then you use the NC one. So your symbol or initial will be this one, and your final will be here. So then you use the NC one.
If the final comes the sigma p prime, then we use the OC.
Yeah. Then you use the OC one.
Okay, thank you very much.
Okay. Maybe let me just try to maybe spend some time to do a revision or summary of the lecture 6 or 9, 6 or 10. Maybe for you have a good preparation of the final exam. Does that sounds okay?
Yeah.
Please. Yeah.
Yeah, that sounds great.
Yeah. I haven't just prepared any slide, but maybe let me just do some hand raising on the blank side. So for the lecture 6, for the final exam, seems to me there will be the four main questions. So 1 to 2, that's the relates to the lecture 1 to 6, lecture 1 to 5, and questions 3 and 4 will be related to the lecture 6 to lecture 10. And for my part, for the 3 and 4, so we have 2 big questions. So each question maybe contains 3 or 4 sub questions. So it will mainly cover all the lecture contents in the lecture from lecture 6 to lecture 10. Is that clear? So only 4 big questions. Normally it will be all 4 big questions for the final exam. So for the main content of lecture 6, so firstly you have to learn how to draw the flow nets. So flow nets. So this one you have to do some trials or practice yourself. So in the final exam, you are required to draw in a blank paper of the flow nets, and then just upload to the system, to the views. So for the lecture 6, firstly, you need to know how to draw the flow lines. So you have to follow the rules. So you draw the flow lines. It's normally 3 or 4 flow lines. That's already enough, 3 or 4 flow lines. And then you draw the equipotential line. That will be the perpendicular to the flow lines. And they roughly form a square, roughly everywhere. And then one important part is once you get the flow lines, you need to know how to get NF and ND. So that's the number of flow tubes and also number of head jobs. Then according to this one, you are able to work out the flow rate or the C page, the so-called C page. Q equal to K times NF divided by ND times their H. So you need to use this formula to work out the C page. What I discussed right now, that's all the main points of each lecture. So hope you can just get some hints to prepare your final. So the C page calculation and how to count NF and ND, that's all very important. And next one, once you just get the flow lines, then you have to know how to work out the water height, the H of each equipotential line. So you know the total number of head jobs, and you know the head difference between the upstream and downstream. You can work out the head job between each equipotential line. So you can work backward on the water height of each equipotential line. So that's water height calculation. H. And also you need to know how to work out the pore water pressure. This is another really important part. So because you have the formula here, the water height equal to U divided by gamma W plus A plus Z. You have this formula, and this is Z. So this formula, that's the total height equals to the sum of the pressure height and also the elevation height. And this elevation height, be careful about that. This one only relative to your datum. So once your datum is fixed, then your Z will be fixed. And this gamma W, that's obviously that's a constant, 9.81. So once you work out the total height, you are able to get the value of pore water pressure at any position. So pore water pressure could be upward or downward. If upward, that's upper lift pressure. So we already lots of practice in the tutorial 6. So you can go back to review the tutorial questions or the lecture or even lecture examples. So that's for the isotropic. For anisotropic formulas, you need to learn how to work out the alpha and then KEQ. So alpha, so KEQ will be the equivalent permeability of the soil. So an alpha help you to convert from the anisotropic case to the equivalent isotropic case. So that's for the so if you get alpha and you can convert to the equivalent or the normal case and do all the previous calculations, you can work out NF and DQ and water height and water pressure. So that's the main points of the lecture 6. Lecture 7. Lecture 7, the main points, the Rankine lateral earth pressure calculation. Lateral earth pressure. So you need to calculate sigma A prime and sigma P prime. Rankine lateral, so you have the formulas to work out the active earth pressure and also the passive earth pressure according to the formula, to those formulas. But before that, you need to work out the sigma V, so the effective vertical stress first, and then sigma V times K. Sigma V times K gives you sigma H prime, or the sigma A prime or sigma P prime. So that's the normal procedure. You need to work out the effective stress first, and then times the lateral earth pressure coefficient gives you the lateral earth pressure. And one more thing is that for some cases, you may have the water table. So if you have some water table on top of soil, then you have to consider the hydrostatic pressure as well. And hydrostatic pressure is always gamma W times H is only relative to the water thickness or the water depth. So, so for the lecture 7, it will be the Rankine lateral earth pressure calculation, and sometimes you have to plus this hydrostatic pressure. It may, you see, may have some 2 layers of soils, maybe the sand 1 or sand 2, sand 1, sand 2, and you are given the gamma and H1, gamma 1, H1, gamma 2, H2. You are required to calculate the lateral earth pressure. So you work out the vertical effective stress first. So according either there's a water table or no water table, we all practice before in the tutorial class or the lectures. You work out the effective stress, and then only times this one with K. For hydrostatic pressure, no need to times K because that's isotropic materials. So, and then you get the lateral earth pressure. So sometimes maybe you are also required to work out the thrust or force. Thrust or force. That will be the pressure distribute, the sum of the pressure distribution diagram. So let's say if you have the passive pressure distribution like this way, then you just calculate the area that gives you the thrust, either a triangle or this rectangle shape. And also the acting point of this thrust force, you use the moment equivalent. To work out the acting point. This one we just take a moment at the top of point A of the normally the surface of the soil. So that's for the lecture 7. So if you just go back to the lecture examples or the tutorial, we can all find the relevant questions. And lecture 8. Lecture 8 it will be the main points circular. So the rectangular loading. Using Phaidon's chart.
Why no circular, sir?
Yeah.
Should do circulars. Yeah.
Which one?
For lecture 8, the circular loading.
Yeah. So the rectangular, that's the first top one priority. So the Phaidon chart, you have to use the Phaidon chart to work out the vertical stress increase due to this rectangular loading. So normally maybe you have two scenarios. One point within this rectangular loading. So you just split into 4 rectangles. So the point of interest has to be the corner of all the rectangles that you split. So that's the most important part. Or if you, for the rectangular loading, if you have a rectangular area, your point somewhere outside, let's say here, then you have to construct some rectangular loading area and do the calculation accordingly. So either sum or minus, but it has to be the corner of all the rectangles that you construct. So that's for the rectangular loading. Or circular loading, that's the second most important part. So if you have the circular loading, if your point of interest is directly below the center of the circular loading, then you refer to the DC point A. Then that you use the formula. We have a formula for any point directly below the center of loading. We have the formula to calculate circular loading. For any point that's not falls on this projection line, then we have to use the influence chart to do the calculation. So basically, it also has 2 scenarios, influence chart. So either the point A or point B, only 2 scenarios for circular loading. So that's for the lecture 8. Lecture 9 is what we learn. So the top or the uttermost important is this one, S equal to mv times third sigma v prime times h. So this is the formula allows us to work out the settlement. So if any questions, so you can find some hints from the questions. If any questions, if mv is provided, it's more likely you are going to use this formula. So what you need to do, you just work out the vertical effective stress increase and times the sample height, and times mv gives you the settlement. That's the most important one. The other important part is Tv equal to CVT divided by d squared. So Tv, that's the one important index, and it has a correlation with the coefficient of consolidation and the time and sample height. This one, it can generate lots of questions. So because the Tv has some correlation with U, if you recall your memory. So either you can find the relationship from the chart or from the formulas, or U or UV. So if you know the UV, then you know the Tv, or if you know the Tv, you know the UV. We have the corresponding formulas. And also you need to remember what's the, when U equal to 50 or when U equal to 90, what's the corresponding Tv value. So that's the very standard value. So let's say if the UV was provided, so for some question, normally the U was provided. Let's say the soil was 50 consolidated then you can easily get the corresponding TV value. And from this TV value and this formula, and this D, you have to decide is either one-way drainage or two-way drainage. Although the odometer sample is always two-way drainage, and this D will be the half of the sample height. For the other case, if it's one-way drainage, then you use the whole sample thickness. So if the layer was bounded by the sand and gravel, so that's all the permeable layer that can be used for the two-way drainage. If a layer was bounded by the rock, the dead rock, or the clay layer, then that's an impermeable layer. Then it's more likely that will be one-way drainage. So you know the D, and if the C-way was provided, then you can work out the corresponding time. So in terms of years, or to reach that 50% consolidation, or if the time is provided in the question, then you may be able to work out the C-way, which is the consolidation coefficient. So that's the very important part of that lecture. Let me think, maybe whether there are some other part, TV or the CVT.
Also,
Yeah.
Can we draw the diagram to one-way drainage and two-way drainage, please?
I draw the diagram.
Yes, yeah. Like an example of the reference.
You see, if it's always the middle will be the clay layer. So if talking about the drainage, clay or the silt. So if below there's rock, or clay. No rock, I mean the dead rock. There's no gap.
Yeah, like there's no water. Yeah.
Yeah, no water penetrate. So which means it will be impermeable layer. So that's the so-called one. So on top you will have sand or gravel. So that's a permeable layer. So that's the two-way. That's one-way drainage.
Yeah.
So on top, if you have sand, you have the gravel, and on bottom is also sand or gravel. So that will be the two-way drainage. And for the calculation, you have to use the half of the sample height. And this one, you use the whole sample height. So that's the D, and this is D, okay? So that's the H. That's H. Is that clear?
Yeah. Wait, so how about the rock section for two-way? Is it a rock or no rock?
Yeah, if a rock, which means no water penetrates through or clay, then there's a one-way drainage. Then you use the whole sample height, whole clay thickness to do the
Oh, like so. Okay. Between two-way, like there's no rock.
No, two-way there's no rock. Two-way maybe it's either sand or gravel, or it will be mentioned clearly. So maybe underneath the clay layer is a permeable layer or impermeable layer. It may be mentioned straight away in text. Yeah. Okay, and on top of clay is mentioned is sand. So you can decide straight away. Okay, and also
two ways half the height.
Yeah, two-way is half the height. So you see a label, the D is the half inch. And also for the same type of soil, the C-way, so there are some implicit information. So same type of soil, the C-way are the same. Or C-way is same. So for some questions, so you see, I take some soil sample from the field and I do some odometer test. And also, so we know the time to reach 50% consolidation. So I'm required to calculate what's the time for the field sample also reach 50% consolidation. So here we need to make use of some implicit information. For the same type of soil, the C-way is the same. So the consolidation coefficient will be the same. So I remember we have one question for this one, the example 2 in the lecture 9. You can go back and review that one. So for the same type of consolidation, so if all required to calculate the time for 50% consolidation, the T wave will be the same as well. And the C wave, if C wave the same, then they can cancel out. Then you can work out the T accordingly. So which means the T wave in the field equal to the T wave in the lab. So if U wave the same, if U the consolidation are the same. So that's for the lecture 9. For this lecture, the utmost formulas is the one because we run out of space. We just the 3 sets of formulas. So S for OC stage, and S for NC stage, and S for.
So can you write down somewhere else, because it's hard to see that? Okay, thank you.
Let me just hide this one. Can you see that?
Oh, we can, yeah.
We just run out of space. So S, maybe 1 is the OC formula, and 2, that's the NC formula, and 3, that's the OC plus NC formula. So that's the utmost important part of this lecture. So you have to work out the initial effective strength and the final effective strength, and also the pre-consolidation strength, the 3 values first, and then you draw the 2 line segments like what I did, you see. And always this is OC and this is NC stage, and this will be the position of sigma P prime. So if your sigma O is sigma O and sigma F or less than sigma P prime, then you use the OC formula. If your sigma O and sigma F prime are greater than sigma P prime, you use the NC formula. Otherwise, if your sigma O prime less than sigma P prime and your sigma P prime or sigma F prime greater than sigma P prime, you use the OC plus NC formula. So that's the most important part of this lecture.
Can you just explain how you actually graph that?
No, I think so this one, I think OC, NC. This one?
Yeah, how you graph it. What is it against?
No, you don't need, can you see the slide, no?
Yeah,
we
I
can
can see that, yeah.
So you don't need to worry about the, so normally it will be the sigma prime, this one in log scale. So this is a log scale, and this is the let me see, that's the void ratio for the settlement actually. But you don't need to worry about the axis. So you only need to know what's the relative position of the sigma P prime. Sigma P prime. So once you calculate sigma P prime, you know it's the same intersection between 2 line segments. Is that clear?
So what, it's from the values that we calculate is against what the void ratio is.
No, it's one value. That's the one you calculated. That's the one you calculated. So let's say originally the line already there is always like this way. Maybe think of this way. The line is already always like this way.
Okay.
Yeah, and then you calculate your sigma P prime. So then you know this turning point, that's the sigma P prime. And next, or in the beginning, you calculate sigma O prime. So you compare this sigma O prime with this sigma P prime. If less than this one, so obviously it's falling somewhere here. And,
Okay.
and also your sigma F prime is always greater than this sigma O prime. If your sigma F prime, you work out sigma F prime is also less than this one, then obviously your initial effective stress and final effective stress all less than the pre-consolidated stress, and then you use the OC formula. Otherwise, if your final effective stress and initial effective stress are greater than the sigma prime, you use NC. And the third scenario, that's the OC plus NC. So this one, we already, you see, those curves are already there. You see, what we need to do, just work out the three values and find its relative position and find the corresponding formulas. That's what we did, you see.
Oh, the curves are already there.
Yeah, it's already there.
Oh, okay.
Yeah, yeah.
I thought we had to work out where the curves were.
No. It's always curve. It's always maybe like this shape. It's always this shape.
Oh, okay, I understand now.
Yeah, okay.
Yeah, I thought we had to work out the curve, and I was wondering how
No,
the value increased and
no.
it was going down.
No. The curve is always the CC and CR is always like this. It's always CR, JCCC, then CR, and it's always provided. And what you need to do just only work out those three values and its relative position and find the corresponding formulas.
Now I get it.
Yeah, yes, find the corresponding formula here. Yeah.
Excuse me, sir. How to, in case the sigma p prime is not given, so how to calculate that?
No, it's ought to be given.
Okay.
Yeah. Otherwise, maybe it has to be given. Oh, for some cases, maybe you are providing us OCR. That's one more thing. So OCR will be sigma p prime divided by sigma O prime. So you see, sometimes it's not given straight away. It will be given as OCR. So let's say if OCR equal to 2, you know the current vertical effect stress. Then you are able to work out the sigma p prime. Sigma p prime will be 2 times sigma O prime. Is that clear?
Yeah, thank you.
Yeah, because here, you see OCR equal to sigma p divided by sigma prime. Sigma prime, you use the current vertical effective stress. So this is another way to get sigma p. So it's either provided straight away or either the OCR is provided. So once you get the current vertical effect stress, you can back calculate sigma p prime.